Hello and welcome to all students. This is the second lecture on Euclidean space, and in this second lecture we study about the inner product in Rn. In first lecture we have studied about the introduction of Euclidean space. In the second lecture we study about inner product in Rn. So let us define what is inner product in Rn. Let x equal to x1 comma x2 comma xn and y equal to y1 comma y2 comma comma yn be any two vectors in Rn. Then inner product of vectors x and y is denoted by x dot y and defined as x dot y equal to x1 y1 plus x2 y2 plus plus xn yn. So here inner product of two vectors, vector x and vector y, is the addition of the product of the corresponding components of vector x and vector y. So the inner product contains n terms. First term is the product of first component of vector x and the first component of vector y. The second term of the inner product is the product of second component of vector x and second component of vector y plus plus the nth term of inner product of vector x and y is the product of nth component of vector x and nth component of vector y. So this is the way of writing inner product of two vectors x and y. Now we note some point here. So first point is, in Euclidean space Rn, the inner product is nothing but the dot product of two vectors, as xi's and yi's, they are real number for all I equal to 1 to n. Therefore the product of real number is a real number. Therefore xi into yi belongs to R for all I equal to 1 to n, and the addition of real numbers is a real number. Therefore x1 y1 plus x2 y2 plus plus xn yn is belongs to R. Therefore, but this is the inner product x dot y. Therefore inner product x dot y belongs to R. Thus inner product is a real number. Okay, so this is about the definition of inner product. So third remark is, inner product in Rn is a function from Rn cross Rn to R. So why it is function from Rn cross Rn to R? Because inner product is a real number, the resultant is in this set, and to take a inner product we use two vectors. First vector is from Rn and second vector is also from Rn. Therefore inner product is a function from Rn cross Rn to R. Two inputs from this set are two inputs from Rn, use one input from R. Okay, so that's why. Now next is, let us take some examples on inner product. First example is, if x is equal to 3, 5 and y equal to 4, 7 are two vectors in R2, then the inner product of vectors x and y is given by x dot y is equal to, so x dot y is equal to, so how to obtain the inner product? By definition, this inner product is the addition of product of respective components of these vectors. So product of first component of this product of first component of this vector and first component of this vector, so 3 into 4 plus Now it is a product of second component of this vector and second component of this vector. So it is 5 into 7. So resultant is 3 into 4 is 12 plus 5 into 7 is 35. So 12 plus 35 is 47. Therefore the inner product of two vectors x and y is x dot y equal to 47, and it is a real number. Okay. Now example 2. Consider two vectors, vector x equal to minus 2 comma minus 2 comma 4 comma 8 and y equal to 5 comma 7 comma minus 1 are two vectors in R3. Then the inner product of vectors x and y is given by x dot y equal to, so how to calculate inner product, that thing is known to you now. So product of minus 2 and 5 plus product of 4 and 7 product of plus product of 8 and minus 1. So minus 2 into 5 is minus 10 plus 4 into 7 is 28 plus 8 into minus 1 is minus 8. So resultant is minus 10 plus 28 plus minus 8 equal to 10. So inner product of two vectors x and y is plus 10. So there are some properties of inner product we state here. So first of all we write the statement of these properties. So statement is let x is equal to x1 comma x2 comma dot 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 comma xn, y is equal to y1 comma y2 comma dot 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 yn, and z equal to z1 comma z2 comma dot 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 comma zn be any three vectors in Rn, and alpha belongs to R be any scalar. Then first property is x dot y is equal to y dot x, or we can say inner product of x with y is same as inner product of y with x. So this property says that the inner product of two vectors is commutative. So inner product of two vectors is commutative. So it doesn't matter whether we are taking the inner product of x with y or y with x, because both the things are same. Now second is our inner product of alpha x with y is equal to alpha into inner product of x with y. Third thing is inner product of vector addition vector x plus y with vector z is equal to inner product of x with z plus inner product of y with z. In other words, we can say that the inner product of vectors is distributes over the addition of vectors. So x plus y dot z is equal to x dot z plus y dot z. We note some points here. So Rn with this inner product is an inner product space. So inner product space is a one special topic which we will study afterwards. The Rn with this inner product is called as inner product space. There are many inner product spaces we will study afterwards. Second is inner product of x with itself is equal to x1 square plus x2 square plus dot 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 plus xn square. Okay, so these two are very important observations. Let us see the property number 1. Inner product of x with y is equal to inner product of y with x, or we can say that inner product of two vectors is commutative. So let us prove this property. So this is the proof of this property. So we first consider the left hand side. Inner product of x with y inner product of vector x with y equal to, so vector x is this, dot product with vector y, and we know that how to find the inner product, or we can say dot product of these two vectors. So dot product of these two vectors is given by the first term is x1 y1 plus second term is x2 y2 plus dot 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 plus nth term is xn yn. But here xi's and yi's, they are real numbers, therefore xi yi is same as yi xi because the product in real number is commutative. Therefore instead of xi x1 y1 we can write y1 x1, instead of x2 y2 it is same as y2 x2, and plus dot dot dot, yeah. So xn yn is same as yn xn. So in the next step we observe that, so by a definition of inner product, so this step we can write it as, a inner product of y with x. So thus we have proved inner product of x with y is same as inner product of y with x. This is the proof of first property. Now see the property number 2. So this property states alpha x, inner product of alpha x with y is equal to alpha times inner product of x with y. So let us prove this property. So we know that alpha x is nothing but a scalar multiplication of a vector x with scalar alpha, and it is equal to a vector with n component, whose first component is alpha x1, second component is alpha x2, comma dot dot dot, and nth component is alpha xn. So we take the dot product of, or the inner product of alpha x with vector y. So alpha x vector is this, dot product with vector y. So by definition of inner product, or we can say dot product, the resultant is, the first term is alpha x1 into y1 plus alpha x2 into y2 plus dot 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 plus alpha xn into yn. But we know that the alpha xi, xi's and yi's, all these three things are real numbers. Alpha, xi's and yi's, they are real numbers, therefore their product alpha into xi into yi, so their product is associative. Therefore instead of writing alpha x1 into y1 we can write alpha into x1 y1. So just we can change this bracket. So instead of taking bracket to alpha x1 we can take bracket to x1 alpha x1 y1. So meaning of this thing is, take a product of alpha x1 and then multiply resultant with y1 is same as take a product of, first take a product of x1 y1 and then multiply resultant with alpha. So both those things are same. So here also we can change bracket plus dot 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 plus, here also we change the bracket, so alpha into x and yn. So first take a product of xn and yn and then the resultant multiplied with alpha. That is the meaning. So from these terms we can take alpha common. So if I take alpha common, so inside the bracket it will remains x1 y1 plus, from this term it remains x2 y2 plus dot 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 plus, from this term it remains xn yn. So alpha into, now this bracketed quantity, now you observe that this bracketed quantity is nothing but the inner product of vector x with y. So finally we have proved, so alpha x, inner product of alpha x with y is same as alpha times inner product of x with y. Now the third property, that is very important. So inner product of vectors distributes over addition of vectors, important. Now let us see the property of this vector. Now see the proof of this property. So proof, we know that we know that the addition vector x plus y. You observe that you observe that the vector x plus y equal to x1 plus y1, comma x2 plus y2, comma dot dot dot, comma xn plus yn. We know this. Now consider the left hand side, inner product of vector x plus y with z. So x plus y vector is here, z vector is here, and we take a dot product of these two vectors. Dot product of these two vectors, how to take that thing is known to you. So it has n terms, and first term is x1 plus y1 into z1. Second term is into bracket x2 plus y2 into z2 plus dot 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 plus xn plus yn into zn. Okay, so now xi's, yi's and z's, they are real numbers. Okay, and multiplication of real number distributes over addition of real number, that is the known thing to us, but we use this property of real numbers here. So we can multiply inside. So if I multiply inside, we get x1 into z1 plus y1 into z1 plus here x1 into z2 plus y2 into z2 plus dot 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 plus xn into zn plus yn into zn. Okay, now in the next step we collect the terms containing xi's together. So we collect the terms which contains xi's. So x1 y1 this term, then take x2 y2 this term, then and plus dot dot plus take x and yn this term. So all these terms we take together, plus now collect the terms containing yi's and take together into bracket. So first term is y1 z1 plus second term is y2 z2 and plus dot dot dot, here we have to write plus dot dot dot. Okay, so plus dot 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 yn zn. Okay, so this first bracket is nothing but the inner product of vector x with z, and the second bracket will represent the inner product of vector y with z. Okay, so see here, we have proved the third property of the inner product, the x plus y dot z is equal to, what do you get is x dot z plus y dot z. Now based on this topic, we have some examples for practice. You can take a screenshot for your own practice. We solve these examples at home. And finally, we stop here. We end this lecture. Okay, thank you.